Eudiometer. Eudiometer. That's what we're going to be focused on. And you felt fancy and you clicked on this lab, and I'm going to show you a fancy lab. And this fancy lab is going to do a eudiometer in order to calculate a couple of different things, especially in the ideal gas equation and gas laws. So all of this stuff, if you take in general chemistry, maybe has already been introduced. We're talking about ideal gas laws, and we're talking about pressure, and we're talking about volume, and we're talking about temperature, and we're talking about the ideal gas equation. All of the greatest things that are out there in that whole realm of the gas descriptions and discussions that you had in General Chemistry 1 and 2, or maybe even in a high school chemistry class or science course. So we're not going to go deep diving, because I could, trust me, but we're going to skim the surface and we're going to focus on the lab and just the lab procedure and what we need to take away from the lab experiment and the steps and why things work the way that they do. And this involves a little bit of gas laws, but again, you want proper discussions. I don't teach Chemistry 151. I used to, but not anymore, but you can find it there. All right, so what is a eudiometer? This is my awful hack job of a eudiometer. That's what this thing looks like. So I want you to think of a eudiometer almost like a burette. It is not made the same way, but as far as shape goes, it's very similar. These are very long, and they could be the length of a burette that you use in a laboratory. So there are long pieces of glassware, and these long pieces of glassware, just like a graduated burette, has these markings on it, and the markings are going to be in terms of milliliters, just like on the burette. And a lot of times these are divided up in 0.1 milliliter markings. That's what the purpose of that scale is going to be, at least most of the time, right? So just like a burette, these markings I can read, and I can record the start, and I can record the stop, but we got to operate these in a little different way. So they are not a burette, okay? Let me just make that clear. It's not a burette. And the reason is because a burette would be very long, and the opening would be up here at the top, just like the eudiometer is. And the burette would have these markings all the way up and down it, just like a eudiometer. And the end of the burette will often have this pointy tip that will drip, drip, drip your solution into a container with a stopcock. All right, so over here for the eudiometer, you need to understand that there's not really a stopcock that we put onto this piece of glassware. It's not needed because we use this in a different way. And actually, the way that I've drawn it here, it's really upside down. So the opening is actually going to go down, and the closed end is going to be up toward the top. So overall, a eudiometer's purpose is to trap and measure something, okay? And what it does really good trapping and measuring are gases. And that is why I said from the very beginning, when I opened this video up and said eudiometer, I told you about gas laws and pressures and volumes and temperatures and PV equals nRT if you've had those science courses before. And this lab is going to make you go back and revisit them. Or if you've not had it, don't sweat, because I'm going to describe every piece along the way that's going to be important for you to know. At the same time, it also seems like a lot of times when these gases are introduced in lecture in a college or science course in high school, they leave off the most important step, and I'll talk about what some of those important steps are a little bit later on. All right. So the eudiometer's purpose is to trap and to measure various gases that we are generating in a lab environment. All right, so let me give you an example. Let's say that I take zinc metal and I react that with hydrochloric acid. Well, that is an acid, and the definition of an acid. Oh, well, let me go back and think about what general chemistry and organic chemistry told me. That HCl is going to spit pew, 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 little hydrogens off in solution. I mean, that is the definition of an acid. So we get this acid, and this acid is like spitting off the hydrogens left and right because that's what acids do. I want you to think of this as a very volatile relationship. Now, volatile means, oh God, don't say anything while you're around them. Oh God, don't look at them the wrong way, because if you do, they'll snap your head off. Oh, don't bring up this, because that's really a sore subject and you don't want them to get into an argument over that. That is the HCl dynamic as far as the relationship goes. So I want you to think of HCl already having relationship problems. And HCl goes into the bar. And HCl is in the bar with relationship problems still. And they're arguing, and they're fighting, and they're cursing each other. And one goes off to the bar and gets a drink, and then turns around and gives the other one the side eye and be like, I'm going to kill you later. I mean, that's what's going on with HCl here. So they do not get along. They want to split as much as possible. And then what happens is, hubba, hubba, zinc comes in, and zinc catches the eye of the chloride. And the reason is because the zinc will often carry a positive or could carry a positive charge, and then the chloride is going to end up carrying a negative charge if that hydrogen goes to the bar and gets a drink and before it comes back. So hubba hubba, zinc comes in and boing, chloride and zinc fall madly in love. All right, so what happens is that the zinc and the chloride will make a compound together, right? And then poor little hydrogen is, oh no, I just went to the bar to buy you a drink because you told me to, and now I come back and you're lip locking with zinc and you're doing it right in front of my face. What on earth? What are you doing? All right, so this is what goes on in reactions. This is bar chemistry at its best, folks. And I promise you, I do not have relationship problems. So zinc and HCl come together, and zinc will replace the hydrogen. So what we will often say is that a single replacement reaction has happened here. And that single replacement reaction means one thing, single, has been, guess what? Replaced. So the hydrogen is getting replaced by the zinc, and zinc and chloride now make a compound, and hydrogen be like, okay, I didn't like you anyway. See ya. I mean, that's what hydrogen does. So this is not quite fixed, though. What if we want to be prim and proper? What will happen is that the zinc carries a positive 2 charge and the chloride carries a -1 charge. So this actually needs 2 chlorides in order to balance out that zinc that brings a positive 2 to the table. And then the hydrogen goes off on its own, but the hydrogen does have relationship problems, and it needs to be in a relationship. And hydrogen will go out and it will look through the bar and it will go, oh, does anybody want to hook up with me? Hello, hello. I mean, that's what it does. And everybody else in the bar, because there's nothing else really there except for chloride and hydrogen and zinc, says, I don't think so. Sorry. And so hydrogen goes off in the corner, and hydrogen takes the cell phone and calls hydrogen's twin. And the hydrogen says to the twin, oh no, I just got broken up with, and I've got nobody else to go out with, and I need a relationship. Would you want to be my partner for at least a bit until I find something else? And that twin says, oh, well, yeah, absolutely. I thought you would never call and ask, hydrogen. So hydrogen actually sees another one identical like it, and it comes together and it makes this H2 compound. And the reason is because this H2, this is one of the things that we call diatomics. Di means 2, atom means atoms. So hydrogen is a diatomic atom or molecule because it never wants to be alone. It always wants to be paired up with something if it is there and if it has access to it. So hydrogen is one of 7. It's not the only one, but it is one of 7. All right, so we get these new products that are formed now from this reaction. We take zinc metal, and zinc metal is going to react with hydrochloric acid, and these two things come together and interact, and zinc goes in for the kill and knocks hydrogen out, and zinc and chloride make a new relationship, and then hydrogen's off on its own. So hydrogen cannot be on its own for the most part, and hydrogen calls the twin up, and these twins make a partnership now that we call a diatomic molecule. So this is what's going on reaction-wise. But the most important piece, and how this relates to our actual laboratory topic, is that one of these products is the H2. And if I take a look at H2, what I'll realize is that this H2 is hydrogen gas. That's how this is going to relate. So we often talk about products getting formed from reactions. We talk about maybe filtering those products and testing them to see what's there. We've talked about products that maybe are liquids, and we can separate those liquids off and testing them as far as boiling point goes, or density goes, or other chemical physical property tests. And now, for the first time, we're talking about products that are going to be in the gas phase. And we can collect them, and we know that they're going to be there. And if I do want to trap them, there's a very clever way that we can trap and capture this product. And this is going to be captured by a eudiometer. All right, so let me kind of draw you a schematic of what's going to happen here. So what will go on in the lab when I decide to do this lab is that I am going to take my eudiometer and I am going to turn it upside down. And the opening of the eudiometer will be down here at the very bottom. All right, so my tick marks are still going to be there. Not a big issue at all. And the idea here is that in order to trap the gas, I need to make sure that it can't escape the eudiometer. And I also have to make sure that I can trap it in there until it's ready to be pushed out. So what goes on is that I will take a bowl, some type of heavy bowl. All right, that's what this is. And I'll take just simple little deionized water. That's it, nothing more. And I'm going to put deionized water into this bowl. Fill it almost full, not quite. If you don't want a bowl, and if there's not one convenient, a beaker will work. So just a very large beaker works great for this process. Fill it full of water and just have it ready for your eudiometer when you get that prepped. Over here to the side, I'm going to take my eudiometer when I grab this in the lab, and I'm going to fill that eudiometer full of water all the way to the tippity top. All the way to the top. I do not want any air bubbles that form here, especially when I turn that piece of glassware upside down. All right, so what will happen is that I will get my eudiometer. I'll fill it all the way to the rim and overflow it if you have to. It's just water, who cares? You're not going to make a mess. Overfill it, and I'm going to put my finger on the top. So that way when I turn this eudiometer upside down, that water is not going to pour out of it. So when I take this eudiometer and I invert it and flip it, then all of the eudiometer will also have water on the inside. And this is where I do not want air bubbles, right? I want this completely full of water all the way to the top. So that way, when I start capturing these gases, the gases can go up to the top of this eudiometer, the gases take up space, and the gases can start pushing that water out as needed in order to take up that space that it needs to. So this is going to be the first part of the setup. And this really is kind of the heart of the lab. A eudiometer filled with water, inverted and submerged into a beaker that also contains water. All right, now in a lot of these eudiometer lab experiments, what you will often see is that they'll say, oh, well, let's take some kind of flask and let's put a chunk of metal like my zinc on the inside. And this zinc and this hydrochloric acid is going to And products are going to get formed, and part of those products are gases. All right, so the gases are going to, up it goes. There's nowhere, it just fills the room. All right, so we got to be careful, and we often will see in those diagrams a rubber stopper that will be plugged up here at the top, and then there'll be a piece of glassware that will be bent, and that glassware will bend down and get submerged under the water. And then that piece of glassware will come back up and it will be pointed inside of the eudiometer. All right, so you need to think of this piece of glassware as having a lot of kinks on the ins or on the outside, so that way it will fit into this beaker or container the proper way, and it can be directed into the eudiometer the proper way. All right, so that's one of the problems with labs like this. Like, how on earth are we going to get the exact right piece of glassware in order for this to happen? All right, I'll talk about that in a minute. But what's happening here is that this reaction is going forward, and this reaction is generating a gas, and that gas is going to escape, and it's going to travel along this piece of glassware up, 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 up into the eudiometer, and it's going to start taking up space. So what happens is that my water will eventually be pushed out. And I know that I filled it full. I know I started with the 0 mark, but that gas is going to take up some space. And when it does, that water is going to be pushed out. And when that water is pushed out, there's going to be a point where it will stop and no more will leave the eudiometer. And that can be read as far as milliliters of gas or milliliters of water that is left over in the eudiometer. All right, so again, read it like a burette, but now I've been able to capture really the milliliters of gas, which is the most important piece here, for our equation that we will use a little bit later on. All right, so I'm going to make this setup a little easier for you. I think that over the course of years, when we've done the lab, we've did away with a lot of the stuff. And by doing that, it's made it very easy to set up and go. Very, very fast reactions here. So for the first thing that we need to talk about is we do away with the piece of glassware. All right. We don't really care about the glassware. It's pieces that can break. It's pieces that can get chipped. And if those do get cracked or chipped, you're going to lose product and you're going to lose gas and your numbers are not going to come out very well. So we just do away with all of that. At the same time, we're also assuming that all the gas is going to leave the container and all the gas will travel through the piece of glassware tubing and up into the eudiometer. And that does not happen. And the longer pieces of glassware, the more problems that we have. So by doing away with the piece of glassware, we actually get better data, not worse. Next up, we don't really use an Erlenmeyer flask either over here to the side. If we did, how on earth are we going to get the gas over into the eudiometer? We're just not going to be able to do that. So we completely get rid of this extra little flask that sits over to the sides of these things. And then what we do instead, and I'm going to draw like a zoomed in piece for you, is that we take our eudiometer, and this is the end of our eudiometer right here. So this would be our opening. And then this is going to get submerged down into some water. So let me be, a little creative and at least put blue here for water or whatever. All right. So what we've decided to do for the labs, and it works out great, don't feel weird about it, is that we take our solid. Okay. In the example that we did, it was zinc, right? All right. So we'll take a chunk of zinc in that case, and we tie it using a piece of thread. And that thread is going to be attached to the sides of the eudiometer with a little piece of tape. That's all that we've got to do. So we're actually eliminating the flask or beaker. We're eliminating the piece of glassware that has to be bent in order to get there. And now what's going on is that we are putting that piece of metal, zinc in this case, closer to the problem area. And that problem area is the bar. And that bar is our eudiometer. So we are attaching that piece of metal here right at the entrance to that eudiometer. So that way a reaction is going to take place, and that reaction will generate gas as a product, and gases have nowhere to go but up. So what goes on is that we start to see gases that get generated in the eudiometer, and those gases are going to be captured because it is right there at the site of where the activity is taking place. No flask, no bent glassware, right at the entrance of the eudiometer. It's going to generate gas, and the majority of that gas is going to go up, not down. And because of that, the eudiometer is going to give you better data as far as volume of gas that's collected. All right. All right, so that's going to be a start in the right direction. This video, of course, is not completely finished as far as the lecture information goes, but it is one step in the right direction. There's more pieces to this puzzle than this, but we're kind of halfway there. So if you take a look at the lab procedure, what you will see is a kind of an abbreviated document that we have wrote over a course of time. And notice here at the top it says obtain magnesium ribbon. So in our example that we're going to do in real life, we're not using zinc, but we're going to be using magnesium instead. So it's still a metal. It's just Mg, not Zn. All right. Then it says cut 2 strips that are about 3 to 4 centimeters in length. That seems very odd to me. I need to double check that. Hopefully I'll fix that, or just double check it by the time that you get it. But that seems very long. I mean, 1 centimeter, that is 2 inches. 2 centimeters is an inch. So we're having some issues with length here. But I'll double check it no matter what. All right. All right, so we're going to cut 2 strips. Number 2, using sandpaper, smooth the magnesium ribbon. It said it should be somewhat shiny, not dull, with no rough spots. So what happens is that this strip will often oxidize on the outside, and it forms this coating or film over the very thin strip of metal. So the sandpaper will allow us to go in and just rough up the outside edges and expose that fresh magnesium again, like the day that we ordered it. Pretty common, not a big deal. We just get rid of that. All right. Number 3, it says after you sandpaper it and get rid of that coating or protective film, then we're going to weight each strip. All right, well, that's another mistake. Gosh almighty, what has happened here? So we're going to weigh each strip, and they should not be greater than 0.09 grams. So that is why I'm saying I believe that 3 or 4 centimeters might be an inappropriate length. But once more, I will double check it. And I will make that correction before you actually do this lab in the lab area. All right. If so, it says cut the strip until the mass is below that target value. Again, no more than 0.09 grams. Number 4, it says fill a beaker with tap water. Now you know, because that beaker is what's going to be used as this vessel down here at the very bottom. So we're going to at least 2/3 full. At least 2/3 full, if not more. So we're going to fill that full of water and have that beaker ready to go. Number 5, it says pour 10 to 12 milliliters of dilute 6 normal hydrochloric acid into a 100 ml eudiometer and slowly fill the eudiometer with tap water. Do not mix it and shake it. Allow the water to travel down the walls of the eudiometer. So very carefully. All right. So what that's basically saying is that for me, this reaction, if I want to talk about that first, is just like the zinc example that I gave you. We're going to react with HCl here. So Mg plus HCl, which is our acid in this reaction, is going to come together in a bar. And H and Cl do not get along. And the Mg and the Cl go hubba, 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 and they fall in love. And we're going to end up with MgCl2 because magnesium carries a positive 2 charge and chloride carries a negative 1 charge. And H2, which is hydrogen gas. And we know it's H2 because it's diatomic and it calls the twin up. And this H2, just like in our example, is the gas. And that is the reason that we are using a eudiometer in order to capture this product, because that's what they're for. All right, so let's talk about the way that we fill this up the appropriate way. With this particular eudiometer step, it's going to say, take my eudiometer just like this, and I'm going to take some hydrochloric acid, and I'm going to add HCl as step number 1. That is 6 normal or 6 molarity strength hydrochloric acid. And it says, you know, a handful of milliliters here. It tells you that in the lab directions. Use the eudiometer to kind of read where that's at. All right, so here is my HCl, and that's at the very bottom. Nothing else is in there. That's it, just HCl. And then it says take a sprayer, and along the edges of the eudiometer, we are going to fill this eudiometer up with water. So in other words, I don't want to spray it in the middle. I don't want these things to fully mix. The HCl is slightly denser than the water. It's going to settle to the bottom as much as possible. And the least amount of disturbance that you can give it, the better off you're going to be. So as the water trickles down the eudiometer, we're going to start to fill this eudiometer up from that moment. And we want to overfill that eudiometer all the way to the top with water. So water is going to sit here, and HCl is still going to slightly be on the bottom. These will not be immiscible liquids. They are miscible with each other. But that bottom HCl will be denser, and it will settle to the bottom, and it will stay to the bottom unless you disturb it a lot. All right, and then what will happen is that we need to attach our piece of metal. We need to get our magnesium strip onto that eudiometer before we do anything else with it. So that's what we'll talk about in the next video. We're going to pick up from here for part 2, and we'll talk about how I get my strip of magnesium in the appropriate spot, so that way I can get really good lab data from this experiment. And you'll amaze yourself. I promise, if you do this the right way. I promise.